So welcome back to our series on gases, and today we're going to look at Avogadro's law. So the combined gas equation, which we looked at in the last presentation, gives us a way to calculate changes in pressure, volume, and temperature. But we still have one issue, and that's dealing with the amount. There are two gas laws relating to volume that are going to help us solve this issue. You would be expected to know these two laws, and the first one is Gay-Lussac's law of combining volumes, and the second one is Avogadro's law. So what does Gay-Lussac's law of combining volumes say? It says, when gases react, the volume in which they do so bear a simple whole number ratio to one another, as well as the volumes of the products, when measured at the same temperature and pressure. So I here have one volume of hydrogen gas react to one volume of chlorine gas to produce two volumes of hydrogen chloride gas. So these are the ratios in which they interact with. So here it's a 1-to-1 ratio. It's not 1.35 react to 2.69. No, they're simple whole number ratios. So knowing the ratios in which they interact, if I put in 2.5 liters of hydrogen gas and I reacted with 2.5 liters of chlorine gas, I would expect to produce 5 liters of hydrogen chloride gas, given the ratios in which they interact. So Avogadro then recognized the implications of the law of combining volumes in terms of atomic theory. And he hypothesized that the volume occupied by a gas at a stated temperature and pressure will be proportional to the number of gas molecules or gas particles, and thus the number of moles of a gas, which is represented by the symbol M. Mathematically put, we would say that volume is proportional to the number of moles, or that volume is equal to a proportionality constant, the symbol A for Avogadro, by the number of moles. So Avogadro's hypothesis states, at a given temperature and pressure, equal volumes of all gases contain equal number of moles or molecules. Experiments show that 1 mole of an ideal gas, and we'll discuss ideal gases more in the next presentation, but every time you're dealing with gases, we are considering them to be ideal gases. And what we're saying is that 1 mole of your ideal gas occupies a volume of 22.4 liters on the absolute scale of 273 Kelvin and a pressure of 1 atmosphere. Now remember that our temperature is always given an absolute scale. So you will always use a temperature of 273 Kelvin. However, you can use different units of pressure. Here I have 1 atmosphere. The equivalent of 1 atmosphere is 101.325 newtons per meter squared, which is a Pascal. So just to be aware of that. These conditions that we're looking at are known as standard temperature and pressure. So when I have 273 Kelvin and 1 atmosphere, and this volume here is known as our molar volume. So we can calculate the volume occupied by a gas under any other conditions of temperature and pressure from the volume at standard temperature pressure using our combined gas law. The volume at STP can be calculated from the number of moles now. So now we can use the amount, we can convert it to volume, in the sample. So we have a molar volume, 22.4 liters. Let's have a look at an example of where we would use the combined gas law. So what volume is occupied by the amount, being 3 moles, of helium at 25 degrees C and 0.75 atmospheres? So let's put in our equation for our combined gas law, which you know is P1V1 over T1 is equal to P2V2 over T2. We have an amount. And if we have a look at our combined gas law, there's no amount there. So what we need to do is convert our amount to a volume. That's the first thing. So let's have a look at our STP. We know that the volume is equal to 1 mole is equal to 22.4 liters. I have 3 moles in this instance, so we multiply the 22.4 liters by 3. That gives me 67.2 liters. My STP, so my standard temperature, will be 273 Kelvin, and my pressure at 1 atmosphere. Now remember, I said there's different pressure units that you can use, but because I'm using atmospheres here, I'm going to use the standard pressure as also atmospheres. That's why I put them together. In doing so now, I should be able to fill that in. So my P1, which is my standard pressure, 1 atmosphere. My V1, which I calculated, is going to be 67.2 liters. And my T1 is going to be my 273 Kelvin. All that's going to be equal to my P2, which I know is 0.75 atmospheres. My V2 is what I'm trying to work out. And my T2, I have a 25 degrees C, which you know has to be converted into the Kelvin scale. How do I do this? You add 273 to the degree value, which turns out to be 298 Kelvin. I rearrange or transpose this equation to get V2, my unknown, on its own, and my knowns on the other side. So there's my P1 and my V1. My T2, as you can see, when it comes to the other side, becomes multiplied by the P1 and V1, which is my 298. This then becomes divided. My P2 becomes divided when it moves to the other side of the equation, so it's then multiplied to my T1 here. So I have 1 atmosphere multiplied by 67.2 liters, multiplied by 298 Kelvin, all divided by 273 Kelvin upon 0.75 atmospheres. When you put all that into your calculator, then you will get 97.8 liters. Just so you know, it is a volume, and we're measuring the volume in liters. The 2 kelvins on the bottom and the top cancel out. The atmospheres on the bottom and the top then also cancel out, meaning your remaining unit of measure will be liters. Just to show you when we use different units of measure, so let's have a look at this one. What volume is occupied by 2 moles of nitrogen at 300 Kelvin and 1 by 10 to the 5 Newton per meter squared? So we're dealing with a Pascal here for pressure. Now I wouldn't have to put in the 1 by 10 to the 5. Sometimes it's just written as 10 to the 5 Newton per meter squared. So you would be expected to know it's actually 1 multiplied by. Again, let's start with our standard, our P1, V1, and T1, which we have. We know our T1 is our 273 Kelvin. We know our P1. In this case now, I can't use 1 atmospheres because I'm looking at my pressure over here and it's newtons per meter squared. So my conversion for that then is 1 atmosphere is equal to 101.325 newtons per meter squared. So I'm just going to fill that in now as my P1. So there's my P1. My V1 I can calculate. 1 mole at STP is 22.4 liters, but I have 2 moles, so I just simply multiply it by 2 to give me 44.8 liters. So I now have my P1, V1, and my T1. What is my T2? It's 300 Kelvin. That's my change. What is my P2? My P2 is 1 by 10 to the 5 Newton per meter squared here, and I'm looking to work out my V2. So I transpose this equation so that again I have my V2 on its own and all my knowns on the other side. And we then simply fill in what we have. So here, if you've noticed, see, I have my 101.325 Newton per meter squared. I just put that into scientific notation. So I've moved my decimal place 5 places to the left, hence it's 10 to the 5. Okay, just to make it simpler for calculation so you can see the relationship now between them. So I have 1.01325 by 10 to the 5 Newton per meter squared, multiplied by my 44.8 liters, multiplied by my 300 Kelvin, all divided by 273 Kelvin, which is multiplied by 1 by 10 to the 5 Newton per meter squared. Now, as you can see, it doesn't really matter what sort of units of measure that we're using once they are all the same, because here the pressure, Newton per meter squared, cancels out this Newton per meter squared. The Kelvin on the top and the bottom also cancel out, leaving the only unit of measure there in liters. Okay, so that's how we know our unit of measure is liters. So if you multiply all these out and put these numbers into your calculator and divide by your 273 upon 1 by 10 to the 5, you will get an answer of 49.88 liters. I want you to have a go at this one yourself. So what volume will 7.5 moles of oxygen gas occupy at 65 degrees C and 1.5 by 10 to the 5 Newton per meter squared? So pause this video using your combined gas law and see do you get the answer of 140.5 litres. Remember the calculations will be on the following slide so you can check your answer there. So here's the solution for that problem. So first of all, we had to convert our number of moles into a volume if we're using the combined gas law. So we have our P1 V1 over T1 is equal to our P2 V2 over T2. Our V1, we know that 1 mole is equal to 22.4 litres under STP, but we don't have 1 mole, we have 7.5 moles, so I multiplied 22.4 by 7.5, and I end up with 168 litres. So that's my V1. What's my T1? Will be 273 Kelvin. And what's my P1? Well, here's I need to have a look and see what pressure units were being used in the problem. And I see Newton per meter squared was being used. So I will use the standard pressure in Newton per meter squared, which we know to be 1.01325 by 10 to the 5 Newton per meter squared. My P2 I am given, which is 1.5 by 10 to the 5 Newton per meter squared. My V2 I'm looking for, and my T2 I was given at 65 degrees C, but I need to convert it to Kelvin, and that will become 338 Kelvin. I rearrange my combined gas law equation so that I have my knowns on one side and my unknown, which is my volume 2, on the other side. I simply put all the numbers in. I check my units of measure. I see I have a Newton per meter squared on the bottom and the top, and they cancel out. A Kelvin on the bottom and the top, they cancel out, meaning my final answer will have a units of measures of litre. When I put all these numbers into the calculator, I find that my answer should come out at 140.5 litres. So that's how we use the amount and convert it into volume and use the combined gas law to solve problems. So that's it for today, and in the next presentation we're going to focus on the ideal gas law. Thanks for joining me.